fit the Sugar One payload into the rocket. So we're here for the next 4 days at Penn State University with the WRX-R team who are going to take us through what's happening. As we know, Sugar One is catching a ride on the WRX-R sounding rocket, whose primary mission is to launch an X-ray telescope into space to see the Vela Supernova. I'm here with Dr. James Tutt, hello, and he's going to take us through how the X-ray telescope works.
Okay, so this is a model that we have made of our telescope. This is our section. Up the far end we actually have the nose cone where you have your telemetry systems and your parachute. That's so that we can talk to the ground, and so that when we hit the ocean we don't hit too hard. And on the other end we have our motors, our rockets that get us up into space. Once we get into space, we're spinning on our way up to keep our trajectory accurate. But then when we get into space we lose that angular momentum. We stop spinning by dropping weights and we open our shutter door, which is this part here. So if we make that go away, this gets exposed to space. And so if we look in the front, this is what the X-rays will see. We have our star tracker. This is our star tracker here, which has a known star field programmed into it. And so it's able to recognize where it is on the sky, and this makes sure that we're pointing in the right direction. We then have the secondary instrument that's being made by the Czech Technical University. This is an experiment based around something called lobster eye optics.
Okay, so that's a different separate payload. Just as in Sugar One is a separate payload, that's another separate experiment that's going on board.
Exactly.
Okay.
And then we have our main experiment. The first thing that you see is our collimator. So traditionally with an X-ray optic you will have focusing plates that take the X-rays and bring them into a point. But they're quite expensive and quite hard to build. So what we use is something called a wire grid collimator. So you have a series of plates that go further into the payload, which I can show you by getting rid of this.
Oh wow.
So it goes all the way down this way, and for each grid you go down, the gap between the wires gets closer and closer together. This means that only light that will actually focus on our focal plane gets through our collimator, and so it's a way of bringing X-rays naturally to a focus. Very easy to build and very cheap. Then we go into our main assembly. So I'm taking away the exterior skins. These are the sections of the rocket that go on the outside, so they are directly exposed to space, and they keep the rest of our payload safe. We have a pumping port here, so on the ground we can evacuate our rocket, because for X-rays to move through our telescope they have to be travelling in something close to a vacuum.
Oh, okay.
And then we have the back side of our collimator. So this is where our gratings and mirrors go. So our gratings diffract these X-rays that are coming to a focus, the same way that optical light would be diffracted by a prism. So we're generating an X-ray rainbow. So you have this collimating light that hits the grating and then are diffracted into an arc. Now this produces lines of X-rays of the same energy, but these lines are very long in one dimension. And so because our detector is reasonably small, we then have a series of mirrors. And these mirrors take the lines and make them much shorter, so that more of the X-rays will fit onto our detector. Because we only get to observe for about 5 minutes, and so the more X-rays we can get, the better.
Excellent.
And we have to stack them this way, because if you imagine a mirror with optical photons, the light can hit the whole of this area and it will reflect. In the X-ray we have to be at a very shallow angle, because X-rays don't reflect very well. And so in projection that's much smaller, so we have to stack them in order to have the right amount of effective area.
And are you going to be getting data real time?
Yes, the data will be coming down. I think it's 2 seconds per read, and so we'll be refreshing on about a 4-second rate. So we should know if we're pointing at the right thing. Then we move down the other end, so if we get rid of the rest of these exterior and interior skins. And this is our detector bulkhead. So we have a gate valve, so I can actually make this transparent. We actually have a gate valve just here. This seals off our camera from the rest of our payload. The camera has to be cold so that we don't get too much charge build up while we're not observing anything.
How cold, like what temperature are you anticipating it will will go to when it's like maybe its highest point?
Sure. When we're looking at space, we'll be looking at the coldness of space, so that will be a few Kelvin. The temperature of our payload actually won't change that much.
Oh, okay. That's fine.
But the camera that we have will be running at minus 80 degrees C.
Wow. Okay.
So we have to keep that separate from the rest of the payload, because we're only allowed to evacuate through that pumping port I showed you.
Yeah.
Up until about 2 hours before launch.
Right.
And so there's a chance that we could leak up, and so we have a separate pump for our camera chamber to make sure that we stay cold.
Right, that you remain stable
Yep.
temperature. Right.
And so when we're on target, we open the escape valve, which means this bellows here. We can get X-rays all the way up and through, and then we enter into our electronics section. Okay, so there's quite a lot of stuff going on here. Most of it's just electronics to make things work. But in this blue box here is where the camera is actually kept. And I can probably make these things go away. And so you have this orange thing. This is the copper cold finger. That's what we cool down with liquid nitrogen when we're on the ground. It's large enough so that it will stay cold enough for the duration of the flight. And then on the bottom, we have our actual camera, which is that square there. And so this is 35 millimeters by 35 millimeters. It's basically a CMOS detector, so very similar to the camera you have in your mobile phone, but scientific grade, so much more accurate. So that reads the X-rays hit, they're detected by this, and then the signals are read out by all of the electronics here. They go to the telemetry, and then they get sent to the ground so we can see what's happening.
Excellent.
And then up here, of course, is the Sugar 1 payload.
Excellent.
And so yeah, that's basically what's going on in
a nutshell.
in our payload.
Tell us more about how you got involved in what you do.
Okay, so I finished my undergraduate master's at the University of Manchester. Decided I didn't want to stay in science, so I actually went travelling, and then started working for a company called E2V Scientific Instruments. Worked there
That was back in the UK.
That was back in the UK.
Yeah.
Worked for them for a year, and then found out that E2V actually sponsored a PhD program at the Open University. So I went there, started working on charge-coupled devices and other silicon-based images, and during that there was a collaboration between NASA and ESA on a mission called the International X-ray Observatory.
Wow.
Through that, I met a guy called Randy McIntyre,
Oh, who is the
who is
PI on this?
the PI of this mission. Got to know him pretty well. At the end of my PhD, we were actually on a conference together in Amsterdam. Went out for dinner and drinks, asked him for a job, and he remembered the conversation. And yeah, things just kind of fell into place from there.
That's excellent. How long have you been here in the States now?
3.5 years. So originally the University of Iowa,
Right.
and then we moved to Pennsylvania State University a little over a year ago.
Yeah, so the whole group moved from Iowa
Yep.
to here. Take us through a typical day here at the office.
I get in early because I like mornings, and there aren't very many people around, so all of those annoying administrative things I can get done. And then yeah, people start coming in and we start finding problems, typically.
Right.
And so we try and come up with low labour intensive, cost effective ways to fix those problems. Often they aren't easy solutions, and we have to get things remade or we have to buy new parts.
Right.
And yeah, we just work through the day working on how to do the next bit of the rocket. We never have enough time, we never have enough people, and we never have enough money, but we get there in the end.
Yeah, you get them, yeah. Is this the only project the group's working on at the moment, or are there several others?
So the gratings that I was talking about, that we align, that's an ongoing project to try and improve how good those gratings are.
Right.
Which goes on, we have a nanofabrication facility on campus. So we make our own gratings there, and we have a few more rockets in the pipeline. So I'm involved with another one called the Off-Plane Grating Rocket Experiment that's due to launch in 2020. And then we've recently been awarded a grant for another 3 rockets that will be staggered over the next 5 years.
Well, thank you very much.
That's all right.
And good luck with the mission.
Thank you very much.